All right, so for number 5, the last one, we have that a large closed container in the shape of a half cylinder with a rectangular lid. So this whole thing is a half cylinder and it has a rectangular lid on the top, is to be constructed with a volume of 0.8 meters cubed. And so the volume inside all of it is 0.8 meters cubed. Okay. It has a length of L meters, which is this guy here, and a radius of R meters, which is this guy here. See? So radius, radius, radius. See? Okay, so all of those are R, whatever, there's my radius. See? All right, cool. For part A, we need to find an exact expression, okay, for L in terms of R and pi. All right, interesting. So what is L? L is the length of meters. See? And I know some of you right now might be thinking, damn, what the heck do I do? Well, what is the context of the problem? What are the keywords? Let's read it again. A large closed container in the shape of half cylinder with a rectangular lid is to be constructed, blah, 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 volume of 0.8 meters cubed. Has a length of L, radius of R. So we have shapes and they give us the volume. Okay. Your formula booklet, does it have something that it can help? Why, yes, of course. The formula booklet, you guys, oh, by the way, important to get used to it. The day of the test, you got no sleep, but you do have your formula booklet and you do have the graphic calculator. Get familiar with the formula booklet. It's a tool that you can use. Go down, geometry and trigonometry, page 6 and 7, 6 and 7. So here I have a bunch of volumes, see? What was I dealing with again? We were dealing with half a cylinder. Volume of a sphere, cone, right pyramid, cone. Okay, so there I do not have the volume of a cylinder, unfortunately. So let's look again, maybe up here. For some reason, it's for numbers and algebra. I don't know why, but this is all, I mean, in prior learning. This is why it's important to get familiar with the formal booklet to know what's in it. I know that the volume of a cylinder is in here, I just wasn't sure where. So I keep digging, I keep trying to find, bada bim, bada boom. Volume of a cylinder, there it is. So volume of a cylinder, let me just write it down. Volume of a cylinder is pi r squared times h. Now this is the volume of a full cylinder. So the volume of a half cylinder is the same thing, just that divided by 2. So the volume that we will be working with is pi r squared h, all of it divided by 2. So this is the volume of half a cylinder that we're going to be working with today. Now what do I know about this equation? So they tell us that r is the radius and h is the height. Alright, but kiddos math, here we're working with L. Okay, but this container, which is half a cylinder, which is on the floor, yes, this is length, but if you stand it up, it's going to look something like this. Yo, my art skills today. Look at that. God damn. So if you draw the cylinder, okay, it's going to look something like that, right? There's your cylinder, and this L, which is this part here, what does it look like? It's the height. So because of the context, important to understand the context of the question, this h is really just going to be L, see? And what is our mission? Well, we need to find an exact expression for L in terms of r and pi. Now, what is that trying to tell me more intuitively? Is that you want to reach L equals r something something, pi something something, okay? Why does it help to look at it this way? Because all you really need to do now is get L alone from here. Get L alone. That is the compass, see? That is your north. Try to get L alone. Why get L alone? Because they tell you. Find L in terms of this and this. So find L equals something. this and this. Okay, cool. So from here, well, first things first, volume is 0.8. So I can start off by saying 0.8 equals pi r squared L divided by 2. Get L alone. First things first, I would multiply by 2. So multiply by 2 to both sides, bada bam, bada boom. 0.8 times 2, trust me on this, it's going to be 0.8 times 2. About 1.6. 1.6 equals pi r squared L. You still need to get L alone, right? What is bothering L? Pi is bothering L, and r squared is bothering L. So I can start by dividing by pi to both sides. So this goes away with this. I end up with 1.6 divided by pi equals r squared L. Okay, how do I get rid of this r squared? Well, what is r squared doing to L? It's multiplying. So again, divide by r squared, divide by r squared, which I know looks kind of weird, but technically it's just going to go on the bottom with this pi. So bada bing, bada boom. I end up with final answer L equals 1.6 divided by r squared times pi. Here I have L equals something something r something something pi. I don't care how it ends up. I just care that L is alone. See? Cool. So that, you guys, is quite literally part A. Not that hard, right? Just gotta go slow and understand what the formula booklet has, what it offers, etc. So this is gonna be for part A. Cool. Then they tell us that the container will be constructed using two different materials because they want to make this question hard. The material for both the curved surface and the rectangular lid on the container costs 4.40 per square meter. So this part here, right, which also goes all the way around, right, is going to be 4.4, and this guy up here is also going to be 4.4. See? Then it tells us the material for the semicircular ends of the container, okay, will be P per square meter. So what's in green costs P per square meter, which is also the green that is back here hidden as a semicircle, right? Okay, so that is what they're trying to say. See? So the cost C of the materials to construct the container can be written in terms of R and P, where P is greater than 0 and R is greater than 0. Okay, sure. For part B, we need to show that the cost of the container is this whole thing here. See? You guys, whenever they put the word show that, it means that this is a fact. Okay? And so it can also be a hint for how you need to build it or construct it. Okay? But basically, you need to reach this. See? So start from C, right? Try to construct yourself the cost of all these curved surfaces to find this C here. See, that is like the big challenge. Now, why am I taking a mini break here? Because when it says show that, and this is a fact, that means that for finding the derivative of C in respects to R in part C, you can use this. And so, interestingly, when it says show that, and you take it for granted as a fact, you can skip part B and do part C. Now, of course, try to get all the points possible. This is worth 4 points. Hopefully, don't skip it. But if you're low on time and you see the derivative and you're like, damn, I know I can do the derivative quick, but I can't do part B, ladies and gentlemen, you don't need to do part B. You can do part C, get those 3 points, and not have time to do part B and not get 4 points, but whatever, man. You're getting points where you can. See? So that is just a small hint. When it says show that, and whatever you need in part C, you use from part B, and this thing is show that, well, you can just do part C immediately. See? So there's a quick hint in case you're low on time and you notice something says show that and you can do the thing right next to it. Consider that. See? Just want to give you all the tools possible for whenever you face the IB. So, we gotta find a way to express the cost. See? Now, keywords. See? Blah blah blah. Because we're talking about the surface, okay? Because we're talking about a surface, we are talking about surface area, okay? Think about it this way. Take this shape, dip it in chocolate, and see all the ways in which the chocolate covers it. Okay, that is all the surface area you need to account for. See? So what surface area am I accounting for exactly? Well, on the one hand, and actually we're gonna need a lot more space for this. So, all right, and so from here, we can notice a couple things. Yes, it's one rectangle plus two of these, right? Plus that half sort of area thing. See? All right, and also these have different costs associated because the IB is a little bit mean and they say they use two different materials. And so, what am I trying to say? I'm trying to say that the curved surface, so that is this guy, and the rectangular lid, which is this guy, both of them have a cost of what? 4.40 per square meter. So, because it's a cost function, I need to multiply these by 4.40. So 4.40 times, and over here I have 4.40 times. See? All right, cool. On the other hand, the semicircular end, which is this guy in the middle, right, has a cost of what? Of p per square meter. So I know it sounds a little bit weird, but over here I'm going to put times p. All right, and so now I just need to dig into the formula booklet and try to find the area, so the surface area for each of these. See? So on the one on the left, well, I have 4.40 times the area of a rectangle. Now the area of a rectangle, right? And I'm pretty sure this is not in your formula booklet. So here you have area of a lot of stuff. Maybe parallelogram can kind of fit here. Whatever, it's base times height. See, so you have a rectangle. I don't know, this is 2, this is 3. The area is going to be 2 times 3. Okay? Yeah, in this case, the area, I mean, my dimensions are L and R twice. So here I have R, here I have R, so it's going to be 2R. See? Just to leave it very clear, this is L, and over here is 2R. So let's write that, L times 2R. On the other hand, I have, well, plus 2P times the area of half a circle. So what is the area of a circle? Formula booklet, area of a circle. There it is. Area of a circle is pi r squared. Now notice, this is the area of pi r squared. This is the area of a full circle. So what is the area of half a circle? You take this guy and you divide it by 2. That's that. And last but not least, I have the area of this sort of like cylinder part. See? So what is the area of the curved side of a cylinder? All right, that is insanely specific, but so is the formula booklet. So here we have area of the curved surface of a cylinder, and as we can see, right, it says 2 pi rh, right? And you might already be thinking, okay, but what is h? We already had that discussion. H is the height of a cylinder that looks something like this. See? So this is the area of a cylinder. I mean, sorry, the height of a cylinder is this. See? But in this exercise, this was tilted sideways, right? And so h was kept here, and they cut it in half. They cut it in half. You end up with something like that, ¿cierto? It got cut in half, right? But h is still h. See? H is still h, h is still h, h is still h. And in this context, they called HL. See? Just because it's tipped sideways, but technically it's still the height of the cylinder if it were standing up. So this h is really just going to be L. That means if I follow the formula, we're going to have 2 pi RL. Now, important point, much how over here we had half a circle, here This is the area of the full curved surface of a cylinder. Our cylinder, as they tell us in the exercise, keyword, we are dealing with half a cylinder. So this formula, we gotta divide it by 2. Quite literally, over here, gotta divide by 2 because it's half a cylinder, not the full cylinder. So now, ladies and gentlemen, I am ready to go ahead. All right, so cost equals, on this left side, I have, well, this 4.40 can interact with this 2, so I end up with 8.80 L times R, see? Then over here, this guy can go away with this guy because of fractions. I end up with pi R squared P. And here on the right side, well, this guy can go away with this guy, simplifies my life a little bit. I end up with 4.40 pi RL. And right now, we're pretty happy. This looks pretty comfortable. I go ahead, I look at what we need to show. Does it say? It says something a little different. See? It says something a little different. So you're probably gonna come here, look at this and say, damn, dude, I suck at math, dude. I'm so far away, man. Fuck. But really, take a moment, take a breather, and look at it more closely. What is the main difference between this here in part B and this that I have here? What is it? Ah, there is no L here. And here there is an L. There's an L here. There's an L here. What is the way in which I can express L? Ah, in part A, we found the exact expression for L. Look at that, how convenient. So L equals, let me write it up here, L equals 1.6 divided by R squared times pi. And so once again, ladies and gentlemen, as you've probably seen in my videos, sometimes, but not always, sometimes part B uses something from part A. And that can be a massive hint going forward. It's not always the case, but take a second and think about it, because if you think about it, it might certainly become very obvious what you have to do. See? So go ahead, plug in L. We have that C equals 8.80 times L, which is, yeah, sure. So this L is multiplying everything, see? Notice how 2 times 3 times 4 gives you, damn, I'm slow today, gives you 24, see? Which is the same as 4 times 3 times 2. I mean, you might have been thinking, okay, this gives me 6, this is 4, 6 times 4, 24. Here, you're thinking 4 times 3 is 12, 12 times 2 also gives you 24. What am I trying to say? When things are multiplying, the order doesn't matter. You're still going to end up with 24. Okay, so just to make this easier on myself, I'm first going to write 8.80 times R, and on the last part, I'm going to put times L. And L was, as we said, 1.6 divided by R squared pi. All right, plus pi R squared P, that doesn't change, plus 4.40 pi R, L is at the end, I feel comfortable with that, 1.6 divided by R squared pi. All right, so now I can play around and understand a little bit better what's going on. So, because here we are multiplying fractions, fractions just multiply straight ahead. So technically here you can do 8.8 times 1.6 times R. And at the bottom you're going to have 1 times R squared times pi. Now no one writes 1 times 1 because that doesn't really change anything. Any number times 1 stays the same. All right, cool. So on the left side it looks like that. See? Yeah. The one on the middle, does it change? It does not. Stays the same. There's nothing I can do. Pi R squared times P. And here on the right side, a similar idea. I end up with 4.40 times 1.6 times pi times R. And over here, I have R squared times pi. All right, so now we're nearing the end of this exercise. So on the one hand, I can do this famous 8.8 times 1.6, right? So that gives me 14.08 times R divided by R squared times pi. Here in the middle, pi r squared times p does not change. And here on the right side, I end up with 4.4 times 1.6. So a little bit different. 7.04 times pi times r divided by r squared times pi. Yeah, and now we gotta do a little bit of a math trick. See? So, just so you guys understand really what I'm about to do, if I take this guy here and I show it to you more closely over there. So here I have 14.08 times r divided by, that is an r, divided by r squared. Now what does r squared do? What does r squared do? So if you have 2 and you have it squared, it's the same as writing 4. Okay, yes, but what happens in between? You have 2 times 2. 2 cubed is 8, but what happens in between? You have 2 times 2 times 2. Ah, so if you have x squared, it's the same as x times x. All right, cool. So down here I have r squared, which is the same as r times r. And here goes the pi. Why does this help? Because now I understand that this goes away with this. You end up with c equals 14.08. I have 1r left on the bottom times pi. Ah, okay. So here on the right side, I can do something similar. I can understand that this goes away with this. And the same thing happens. This one gets rested by 1. This one disappears. And so you end up with 7.04 divided by r just once. All right, and so now I'm feeling a little bit more comfortable. Now I have something very, very similar to what I need to reach. I go over here and I see how it's similar. So notice that it starts with the one that has just r. So the one that is just r is this guy here. So let me write c equals, let me write c equals 7.04 divided by r. Then it goes with the one that has a pi on the bottom, see? And this other thing's kind of weird, but we'll get there. See, it has the one that has pi on the bottom. So pi on the bottom is this guy, right? So I'm going to go ahead and put plus 14.08 divided by r pi. And last but not least, I have the triple p pi r. My p is at the last part, but again, 2 times 3 times 4 is the same as 4 times 3 times 2. So I can rewrite it as I please because it's all being multiplied. So I'm going to leave it as the exercise asks. P then pi then r. P then pi then r. See? And here, technically, you're good to go, but I'm sure some of you are thinking like, yo, what the hell, dude? I don't think I know what this is. What the fuck is that? It looks weird, I know, but I got you. Relax, don't worry. See? What the negative exponent does, ladies and gentlemen, is always the same thing. The negative exponent, what it does is flip it. So, negative exponent flips your flips your thing, because it can be a variable, it can be a number, flips your thing. See? Example. 2 to the power of negative 1 is going to be 1 over 2. 2 to the power of negative 2 is going to be 1 over 4. Or actually, the step in between is that it's going to be 2 to the power of 2 equals 1 over 4. So notice how this negative exponent, first, you put the whole thing on the bottom, and then you sort of like do the exponent and end up with 4 on the bottom. See? That is what the negative exponent does. And so if you have x to the power negative 1, you end up with 1 over x. If you have x to the power negative 2, you end up with 1 over x squared. And I know some of you might be thinking, okay, but why? Why does that happen? I never understood. Math is so confusing. Math is oftentimes also called the study of patterns. The big question is, did we create math or discover it? There are so many patterns in this world. Did we find a way to express it, or was it already there? I don't know. But that is a question for another day. For now, let's focus on the study of patterns. See? Example, 2 to the power 3 2 squared, 2 to the power of 1. See? So this is just a mini lesson on how negative exponents work, and you're also going to discover why anything to the power of 0 is equal to 1. See? So mini lesson, you can skip ahead if you want, whatever. 2 to the power of 3, we said is 2 times 2 times 2, which is going to be 8. 2 squared is 2 times 2, which gives you 4. 2 to the power of 1 is just 2, which gives you 2. And 2 to the power of 0 is 1 because you've been taught that anything to the power of 0 is equal to 1. Let's understand why. The reason this happens, you guys, is because, notice, to go from 2 to the power of 1 to 2 squared, what do you do? From 2 to 4, you do times 2. From 4 to 8, you do times 2. But what if you gotta go backwards? What if you gotta go from 8 to 4? 8 to 4, divide by 2. 4 to 2, divide by 2. 2 to 1, divide by 2. So 2 divided by 2 gives you 1. And so in any pattern that you discover, eventually you're going to have the same number being divided by itself, which is why it gives you 1. 3 squared, 9. 3 to the power of 1 is 3. From 9 to 3, you divide by 3. Here you divide by 3 again. So it's 3 divided by 3. It's itself being divided by itself. The same as here, itself divided by itself. Itself divided by itself. You end up with 1. So that is why anything to the power of 0 is equal to 1 because you're dividing it by itself. See? But what if you take it a step further and you say, fuck society, let's keep going. If you keep going, 1 divided by 2 is how much? 1/2. What if you divide by 2 again? So it's 2 to the power of negative 2. You end up with 1 divided by 2, divided by 2 again, so it's going to be times 1/2, which is the same as 1 over 2 squared, which is the same as 1 over 4. Okay, so that is why the negative exponent sort of flips it, because you're dividing, see? Keep in mind that if you have 1 divided by 2 to the power of negative 2, you still flip it. So this would go on top first, so you end up with 2 squared equals 4. What do I mean by this? If you have 1 divided by, I don't know, x to the power of negative 4, you put it on top. If you start off on top, you put it on the bottom. Okay? Different examples, same idea, negative exponents, you flip it. See? This thing about multiplying and dividing, another way you can think about it is that in each of these scenarios, technically you're always multiplying by 1. See? And so, if in this case you divide by 2, you're getting rid of one of them. So there you only have 2. If you divide by 2 again, you're getting rid of another one. And if you divide by 2 again, you're getting rid of this one. What do you end up with? With just 1. That is another way you can think about it. Technically, everything is always being multiplied by 1. See? Alright, whatever. Whatever floats your boat. Just a mini sort of thing to understand exponents. And so over here, if I force you, because again, I'm forcing you because over here it says show that. See? So you got to reach the same thing. If here it has an r to the power of negative 1, we'll put this r on top. Put this r on top. What do you need to do? You want to flip it, right? You want to put it on top. And so you flip it, you put a negative exponent. Kapow. Over here, what are they asking for? They're asking for you to flip just r. Pi doesn't matter, you flip just r. So if you flip just r, well, it's on the bottom, right? You want to put it up top, do the negative exponent, you're flipping it, there it is. Okay, and last but not least, this thing doesn't change. And there is the show that they're looking for. Okay, that was a little bit long, but there was a lot to do and a lot to clear up. See, the biggest thing I would like to show you, or really, really be clear about, I think the best way to find the cost is do something like this. Okay, draw a couple diagrams, color it in, take your time, and be very wary of how the functions change. Okay, I mean how the formulas change. The IB loves to do this. They love to give you half squares. And so you got to consider that it's 2 squares, but the formula changes, you divide by 2. A classic is, for example, this cylinder, right? It's easy to forget that it's half of the whole curved cylinder, so you got to divide by 2. In fact, the first time I did this video, I did not notice. Okay? It can happen to anyone. And then I realized, and I was like, damn, I forgot to divide by 2. See? It can happen to anyone. Take a moment, draw it, consider it, and know that the IB tries to catch you with that. That way you don't fall for it yourself. See? So this part B was a little bit long, but I'm sure it was worth it. So there it is, part B. Part C, you need to find DC over DR. I'm sure some of you are already thinking, damn, what the heck is this? I don't know. DC over DR is, lo and behold, the derivative. See? When you do the derivative, it helps you maximize, find the optimum, find the slope. See? What do I mean by this? Originally, when you have any function, okay? When you have any function, for example, f of x equals, I don't know, f of x equals, actually, yeah, so f of x equals 3x plus 2, see? Technically, right now, if you do like an xy table on this, right, you're going to end up with a bunch of set of points. So if x is 1, y is 5. If x is 2, y is going to be 8. See? And so this gives you sets of points. This gives you 1, 5. This gives you 2, 8. See? The moment you do the derivative, okay, what happens is that now you don't get set of points. But what you will get is that this whole thing is now slope. And this is sort of like, if you plug in, I don't know, x equals 2, now you'd be asking, what is the slope when x equals 2? Instead, before, you were asking, what is the slope, what is the y value when x equals 2? All right, so very different things. The moment you do the derivative, it helps you find slope. And if you plug in anything for x, you're asking the function, what is the slope with this value of x? In this other hand, you're finding the value of y when you plug in an x. See? All right, beautiful. So now we understand a little bit better what derivative does, and further down the line, you're going to understand why it's even useful in the first place. So, finding the derivative of this, well, it's a little bit easier than what you think. And as I said, because it's show that, you can jump to this right away. Why am I saying this? Derivative exercises are usually pretty fast. I gotta be honest, they're usually pretty fast given the amount of points they give. You can probably do this in like a minute and a half, and it gives you 3 points. That is a pretty good investment. So I'm just saying, derivative problems, do that shit right away, get those easy points. I'm just saying. I've always noticed that derivative problems give you way too many points for the amount of time it takes. So we're trying to do the derivative. See, so I'm going to put here derivative. There you have it. Derivative of x to the power of n. Really, what it says here, in other words, is derivative of an exponent. Guys, I have a video on the derivative of an exponent. You can check it out. But very, very intuitively, what we're going to see, and you can see it here as well, ¿cierto? Is that the exponent is going to drop in front, and you will subtract it by 1. That is all that happens. That is literally all that happens. So if you have x squared, and you do the derivative, the 2 goes down in front, so it's going to be 2x, and you do minus 1 to the derivative. So you end up with x to the power of 1, which is the same as just leaving it as 2x. Let's do another example, just so that we're very clear on this. If I have, I don't know, 3x squared. Not 3x cubed, 3x cubed, see? Whoops, 3x cubed. If you do the derivative of this, you end up with 3 times 3 times x to the power of 3 minus 1. So that means I end up with 9x squared. The derivative of 3x cubed is 9x squared. That is the derivative of an exponent. Pretty simple, right? Over here, it looks a little bit more nasty because we have some variables going around here or there, and it's just kind of weird, see? But something cool is that when they did the show that and they asked you to put the r on top, it helps you to do the derivative. What am I trying to say here? Sometimes putting all your variables on top, even with a negative exponent, helps you do the derivative. In fact, that's why they did it this way, to make your life easier. Whoa, AB is trying to make my life easier? Ladies and gentlemen, sometimes they do, to your surprise. And so because you have this r on top, now it's easier to do the derivative of an exponent. If it were on the bottom, and I'm like, do the derivative of this, that's hella hard. But if I ask you, do the derivative of this, that's a little bit more easy, isn't it? ¿Cierto? It's more intuitive how the exponent plays. So now, for finding this derivative, I can do, let me put small thickness. Okay, so this guy is going to multiply in front, so I'm going to have 7.04 times -1, r minus 1 minus 1. So that is the term on the left. See? For the term on the right, it's awfully similar. You're going to have 14.08 times -1. All of this still divided by pi times r. ¿Cierto? This is all the times. -1 to a minus 1. Plus, well, this 2 is going to multiply this whole thing. So you're going to end up with 2 pi r, 2 pi r, 2 minus 1. Okay, so this first term ends up being negative, so negative 7.04 r to the power -2 minus, because there's a minus here, 14.08 divided by pi times r to the power -2 plus the only one that says positive 2p pi r to the power of 1. Because it's to the power of 1, you just don't really write it. So that is part C. Really fast for the amount of points it takes. Super intuitive. Consider doing that right away. Not gonna lie. All right, so that is for part C. Let me just double check that it is okay. Taking a good look. Looks just fine to me. All right, cool. So now for part D, they ask us, or they tell us that. Let me just highlight this for a second. Yeah, there it is. They tell us that the cost of materials to construct the container is minimized. Big word. Big word. Minimized when the radius of the container r is 0.7, and to find the value of p. So here, the keyword is minimized. And now we need to understand a little bit better what derivatives are good for. And so I did tell you just a minute ago that when you do the derivative, you are now talking about slope. Okay, why is slope useful for optimization? So here's a little bit of 101 on why slope is useful for optimization. Sorry, why derivatives is useful for optimization. Hint has to do with slope. So let's say you have something that looks, sure. Let's say you have something that looks like that. Okay? And let's say, I don't know, over here it's production. And up here it's earnings. See? And so maybe you're thinking about how many brownies, you gotta cook for a bake sale and sell them at school. If you make too many brownies, you're not gonna sell them all. You're gonna lose money because some brownies are not gonna get sold, And if you make too little, well, you're not gonna sell enough. People are gonna be hungry, and you weren't able to sell enough for the people. So those are the two extremes, right? Over here is a situation where you make too many brownies, you gotta throw some of them out, you lose money. See? Over here is the case where you did too little and you could have sold more. And over here is the perfect amount where, everyone was happy with the amount of brownies, everyone was fed, and whatever, not one brownie was thrown into the trash can. See? Yeah. How do you reach that point? Well, this point here, ladies and gentlemen, is, in a quadratic, the vertex. See? Guys, a vertex is always one of two things. It's either a maximum or a minimum. In this case, we have, Yes, we have a maximum, ¿cierto? Because it's up here. A minimum would be something that looks like that. See? The lowest point, maximum is highest point. Dale? All right, cool. So, to reach a vertex in a quadratic, there's a couple ways. See? Today I'm going to show you the way through derivatives. And so, there's a key idea we need to understand. When you do the derivative, so you end up with f of this, ¿cierto? This whole thing is slope. See? This whole thing is slope. And so what you can do, right, is understand the following. At this first part, for example, at x equals 1, see, over here, what is the slope? Well, if you draw a line here to signify, oops, let me try that again. If you draw a line here to signify the slope, it looks something like that, see? There it is. This is what we call a tangent, okay? A tangent is something that touches once and never again at a certain point. So the tangent at x equals 1 is a straight line that helps me see the slope. And so if you plug in like this, that's going to give you the slope at x equals 1. It's going to give you the slope of that line. See? Now, if we eyeball it, it's positive, right? And it's growing, so this would probably be, I don't know, it's going to be like 2. See? If I make another line down, and if I find another slope over here, see, and I draw a line here, well, what's the slope of this one, you guys? Well, it's still growing, so it's still positive, but it's a little less, isn't it? So instead of 2, I'm going to put 1, see? And if you keep going and you keep drawing lines until you reach the vertex, all right, here comes like the big O moment, see? So over here, right at the vertex, you have a slope of what? Ladies and gentlemen, you have a slope of, it's a horizontal line. Look at this. Look at my amazing art skills. 0 degrees, boom. It's a horizontal line, isn't it? So m equals 0. Why is it 0? Because gradient, which is the same as slope, which is the same as m, they tell us is y2 minus y1 divided by x2 minus x1. Oops, minus, there we go, minus x1. So, is it changing in my x values, this blue line? This blue line, is it changing in x values? Why, yes, of course it's changing in x values. Is it changing in y values? It's staying at the same one. So, it's staying at the same one, so up here it's going to be 0, and on the bottom it's going to be x2 minus x1. So it's 0 divided by something. 0 divided by something is always going to be 0. So my slope at the maximum, okay, holy shit, someone write that down. My slope at the maximum is equal to 0. And I can do the same thing. My slope at the minimum is equal to 0. So, ladies and gentlemen, if you want to optimize something, find where its slope is equal to 0. Bada bim, bada boom. Couple of hearts, because I'm just saying this is a big thing you just realized. If you want to optimize something, find where its slope is equal to 0. Damn. So the first thing you gotta do over here is that you take dc divided by dr and you equal it to 0. Guys, I shit you not, just by doing that, you get 1 point. You literally get 1 point. And it's a method point, which is knowing the procedure, knowing what to do. So this already gave you 1 point. It's just the idea that I just shared, filled with a bunch of hearts, that gave you 1 point. So take your slope, equal it to 0. Take your derivative, equal it to 0. Same idea. You want the slope of 0 because it's going to help you find the vertex. Helps you find the max or min. Even in a graph like this, you do the same process. So this is going to be, I don't know, a -2. This is going to be like a -1. And here, boom, it's going to be a 0. And later on, sure, whatever, it ends up being 0.5, then it ends up being like, I don't know, 3. See? But m is 0 at the optimum, okay? So, you equal this to 0, and you try to find the value of p. So, if this whole thing equals 0, that means I can say 0 equals negative 7.04, and they tell me as well that r is 0.7 by context of the problem. So I'm going to put 0.7 to the power of negative 2 minus 14.08 divided by pi times, what is r? R is 0.7 to the power of negative 2 plus 2p pi r. They tell me that r is 0.7. And so from here, you can solve the problem a little more easily. See? So we're going to be plugging in a lot of numbers. This is going to take a little bit, but at least now we understand very well what is going on and why it's going on. See? Which is the most important thing you can do. Really understand the intuition of the problem. So let me take a screenshot and let's do some hardcore math because that's what we're here to do. So we're going to need a shit ton of space because this exercise is fucked up, but that's fine. So we need to get p alone. See, and I just plugged in a bunch of numbers. Let's see what happens. So this 0 stays as 0, whatever, ¿cierto? This first term, let's find out. We have negative, actually I can do this whole thing immediately. See? So this whole thing is going to be negative 7.04 times 0.7 squared, right? Squared negatively, sorry, minus, going to put a fraction using alpha y equals to hit f1, 14.08 divided by pi times 0.7 to the power of negative 2, okay, plus, actually just leave it there, so I'm not going to do the last part because I can't, right? But this right here is going to give me negative 23.51. I'm just going to put the whole number, I don't care, 388,408, see? And now I find this last part over here, see what p is. So p is being affected by 2 times pi times 0.7. So I'm going to do exactly that. 2 times pi times 0.7. So I have 4.398229715 p. So you want to get p alone, right? Well, p is being affected by a multiplication and also something being added slash subtracted. So here I can do plus 23, 51388,408 to both sides. Golden rule of algebra, always do it to both sides. So here I end up with 23.51388,408 equals 4.398229715 p. You can do significant figures, but for some reason I didn't. I don't care, whatever. Here I can divide because it's being multiplied. 915. So this goes away with this. Here I divide the 23 by this long ass number. And so p equals this. See, so p equals this 23, well, positive, ¿cierto? So let me just write a positive 23.51388,408 divided by this other number. P is going to equal 5.34 621 5547. Let me just mega double check over here. Oops, that's the formula booklet, wrong one. Let me just mega double check, but it should be right. Yes, it's correct. If you want to put significant figures now, you can count 1, 2, 3. Round it up or down. You round it up because it's a 6. You can leave it as 5.35. Remember your units. Dollars per, what thing? Square meter. All right, so that, you guys, is finding the value of p for part D. Not super hard, but you do need to understand what you're doing, see? The moment you equal the derivative to 0, everything just kind of flows, and I hope now you understand better why. Why did we do it? Because it is the key thing for optimization. If you want to optimize something, as it says here, find where its slope is equal to 0, okay? That is why we start off with this very important step right there. So finding the slope equal to 0. Yeah. Then they tell us that in total, 350 containers will be constructed at this minimum cost, and to calculate the cost of materials to the nearest dollar to construct all 350 containers. So they give us the value of P, right? And each container, how do I find the cost of one container, you guys? So this derivative helps me find the value of P, okay? Which is this thing here, right? But what is the cost of one container? I gotta go all the way back. Gotta go back to my original function for C. Okay, so my cost function, which is what I did all the way over here, is right there, right? And I just found my value of P. So my cost function now changed a little bit just for plugging in P. So P, as we said, just give me a second. P, as we said, was 5.35. So 5.35 pi r squared. So now my cost function changed to this, right? All right, and they also tell you that the container is minimized, right, from this part. The container is minimized when r is 0.7. So I can also plug in 0.7 for r. So all of these can have a 0.7 plugged in. See? 0.7, 0.7, 0.7. And so this, ladies and gentlemen, is the cost of what? It's the cost of one container. See? And I know this looks nasty, but these are all just numbers. I just got to add, subtract, etc. See what happens. Pi is just a very long number. Let's not forget that pi is, you don't have to memorize it, a very long number. See? So, this looks nasty, but it's just numbers. Take it easy. Put it into your calculator. See what happens. So I'm going to have 7.04 times 0.7 to the power of negative 1. Just the 0.7 to the power of negative 1. Careful with that. Then I'm going to be adding a fraction, which goes 14.08 times 0.7, and only the 0.7 is to the power of negative 1. Oops, negative 1. Yeah. And then down here, I'm going to have pi. Easy as that. And last but not least, I'm going to have this 5.35 times the pi times the famous 0.7, this time squared. So what does that give me? This gives me the cost of a single container. The cost of a single container is 24.6895 from my calculator. See? All right, so this is cost of one container. One container. What is the cost that they're asking for? Exactly, they're asking for 350 containers. So you take this one container, you multiply by 350, and you end up with your 350 containers. So take this number, multiply by 350, and there are the cost of your 350 containers, which is exactly 86 8643.39. See? 1397. Now, you're not quite done yet because there is an important disclaimer at the end of this exercise. They tell you that you need to answer to the nearest dollar. So what is the nearest dollar in this case? What is the nearest dollar in this case? So here you just need to round like consciously, right? And so I know some of you might be thinking, oh, here, well, I got to round down because of this 39, right? And so you're going to leave it as 8643. And although you're right from a math perspective, you would be slightly wrong from a context perspective. Because if you're trying to produce these containers, right? And you show up to your manufacturer with $8,643, he's going to say, yo, where are my 39 cents? And so, because of this context, you got to round it to 8,644 because you got to be able to pay the guy. And I know 39 cents, it's like, dude, is he really going to whoop my ass for 39 cents? Some people do. So pay him the extra dollar. Given the context, you got to round it up. See? $8,644. And just so you know, if you got something a little different, right? If you maybe you didn't do these long numbers over here, right? If you did significant figures over here, you can get a slightly different answer, and the IB takes this into account. Just so you guys are a little bit more relaxed, look at the answer key here. It says accept answers between 8641 and 8645 due to routing the value. See? So keep that in mind. It considers, like these small decimal changes and this or that, but because of context, round it up. Okay? Those 39 cents, they matter, and you're answering to the nearest dollar, you gotta put it $1 up. See? All right, that is for part E. And now we're almost done. Don't worry. Part F, they tell us that the materials for constructing the containers can be purchased at a discount according to the information in the table. Yeah. So if the cost of your materials is between $1,000 and $2,500, you have a 1% discount. And as you keep adding more cost to your materials, you get a bigger discount. Why does this make sense? Well, it's actually an incentive. If you put something like this, you're gonna try to have your consumers or whatever ask for more containers, and so your client is gonna ask for more for more work from you, and you're happy with that, cierto? You want your client to be happy. You want him to have an incentive to spend more on you, and so yes, you're making a discount. Yes, you might be losing some money, but think about it this way: if you didn't do any discounts, maybe your client would buy this. See, he would send containers in this amount. But with the discount, your client is more prone to saying, okay, with this discount, I think I would do it over here. And you're both happier because of the discount. See? So that is why discounts exist in the first place, and it also makes sense, right? I mean, the more you buy, like producing in bulk tends to be cheaper. See? Okay, I got a little bit economist there, but it's true. Economies of scale, all of that crap. Yup. Anyways, here we have part F. Determine the cost of materials for 350 containers after the discount is applied. So the cost of materials, as I found out, is 8644. So that means I'm in the range of 8%. And so I gotta do an 8% discount to this amount, the 8644. And so there's two ways to do this, you guys. I'm gonna show you the way I like to do it. So technically, if I do the discount, right, the original price, which is 100%, right, 100%, I'm going to subtract it. Instead of paying 100% of the price, I'm now paying 100% minus 8% of it. See? So what does this mean? I end up with 8644, parentheses, 92%. Now, how do you express 92 as a percent? You leave it as 0.92. Why? Well, 1 is 100%. 0.5 is 50%. 0.05 is 5%, which means that 0.005 is 0.5%. As long as you memorize just some of these, you're going to be able to convert decimals to percent and the other way around effectively. What is happening behind the scenes? You're just divided by 100. See, so 50 divided by 100 gives you 0.5. 5 divided by 100 gives you 0.05. If you don't trust me, well, it's about time you did. 5 divided by 100, 0.05. See? 50 divided by 100, 0.5. So that is how you get those whatever from percent to decimal. Okay. Why do you do it to decimal? Because then you can plug it in to your calculator. So this in my calculator is going to be 8644 0.92. There it is. And so the cost of materials, right? The cost of materials is now going to drop to 7952.48. See? Da, da, da. Give me a moment. All right, sounds about right. See? And so here you get 2 points, one side for method, another one for your answer. See? Now, as we saw before, the answer from part E can oscillate a little, it can change a little, right? Depending on whether you use decimals or not. And so here the method is super important. It's very important that you show this. Okay, find your way to show it, but do it. I'm going to show one more way because I know some people like it to do it a little different, ¿cierto? So what you can do is that you can first find the amount of discount that you get. So for example, if I do 8644 and I multiply it by 0.08, which is 8%, ¿cierto? What is this number? This number is the amount of discount I am getting. It's not the total cost of materials, it's the amount of discount. So I will get discounted $691.52 with this discount. And so you can take your original amount, 8644, subtract it, 691.52, and end up with, lo and behold, 7,952.48. Don't trust me? It's about time you did. This minus this gives you the same number. See? So those are two different ways to do it. You can either find like how much you're going to get discounted and then subtract it from your OG amount, or from the OG amount, find how much is going to be like sort of like the total left. See? So from 100%, you subtract 8%, 92%, put it in decimal, bada bing, bada boom. Guys, whatever is more intuitive for you, stick to it. You're the mathematician here, not me. You're the one that faces the test, not me. Find what works for you, find what's reliable. And the biggest message in all of my videos, you guys, is find the right procedure. Okay, there are method points all over these tests. And if you understand the method, if you understand the procedure, you will for sure get at least a 4. And with a couple marks here or there, you're going to get a 5. Okay, it's that simple. And I know most of you just want a 4 or a 5, so stick to that. Stick to the procedure, learn the formula booklet, learn what's in your graphing calculator, and you're going to be just fine. All right? A 6 or 7 is attainable with more studying, more exercises, but a 4 or a 5 should be certified, you guys. Okay? Graphing calculator, formula booklet, and just a little bit of faith in yourself, and you'll get there. Ladies and gentlemen, that is for number 5, and that is actually for this whole paper too. I hope it helped. I'll see you around.